In this video, we're going to look at what happens when we combine multiple ions together, as well as explain what happens to electrons when an element loses an electron or when an element gains an electron. Now, in order to talk about this, we need to discuss something that has a relatively complicated name, but is relatively simple in concept, and that is what we call the law of conservation of matter. So the word conservation in this case means to preserve or to keep the same. Now, the law of conservation of matter simply states that on Earth, it is basically impossible for us to create or destroy atoms as well as all of the particles that make up atoms, including electrons. So in this case, when we look at sodium and chlorine, we have the basic understanding that because sodium is the element in this pair that has fewer electrons, and again, in element pairings, this is most likely always going to be some sort of metal, it is easier for sodium to lose its one valence electron than it is to gain 7. Now, conversely, chlorine is the element in this pair with more valence electrons, and again, this most likely is going to be a nonmetal when we deal with pairs of elements that form ions, and because chlorine already has 7 valence electrons, it's much easier for it to gain 1 valence electron than it is to lose 7. Now, what the law of conservation of matter states is that the electron that sodium loses is indeed the very same electron that chlorine gains, and this is what we call an electron transfer, or a transfer of electrons, and this is actually how ions form, rather than an electron just disappearing off into space and an electron appearing out of nothing in order to complete chlorine's valence shell. Now, from this, we are able to assemble an ionic compound, and we can actually draw the structure of the ionic compound that we make using Lewis structures. So we remember, if we want to represent a metal in its ion form, we don't show the valence electron because sodium has lost its 1 valence electron, and so there are no valence electrons showed at all, and we represent this with a charge of +1, meaning that sodium has lost 1 electron. Now, since that electron can't magically disappear, we represent that electron on chlorine, and when we draw the Lewis structure of chlorine, we show that it has a full valence shell like this, and we represent the gain of 1 electron with this negative charge here. And together, when we have a positive ion, which is what we call a cation, paired with a negatively charged ion, which is what we call an anion, we have now made an ionic compound. And the other reason why we call it an ionic compound, beyond the fact that it's made of 2 different ions, is because the charge itself of the ion is the force that holds these 2 ions together. Now, because positive and negative are opposite charges, this means that the 2 ions are going to attract to one another, and this positive-negative attraction is what we call an ionic bond. And when we look in more detail at the structures of ionic compounds, we'll examine in more detail what an ionic bond is. Now, what about where we're dealing with situations like this? What about in the situation where we've got a metal and non-metal pair where the 2 do not lose or gain the same number of electrons? So here we can see that because magnesium has 2 valence electrons, it's much easier for magnesium to lose 2 than it is to gain 6. And conversely, because fluorine already has 7 valence electrons, it's much easier for it to gain 1 rather than to lose 7. Now the problem is, if we try to draw the electron transfer like this, magnesium can only give away 1 of its valence electrons in order for this one fluorine to have a full valence shell, but magnesium still has another electron to give away. Now, the intuitive among you will probably say, well, why don't we just have a second fluorine here? Why does it only need to be 1 fluorine? And that intuition is indeed correct. So if we were to have 2 fluorines, that means that magnesium could give 1 of its valence electrons to one of the fluorines and 1 of the valence electrons to the other. Now, how about a consistent algorithm that we can use in order to figure this out? And for those that are mathematically inclined, what we can use is we can find the lowest common multiple based on the number of electrons that are lost and gained between the 2 elements. So magnesium, as we've already seen, loses 2 electrons, whereas fluorine gains 1. And the lowest common multiple between 2 and 1 is obviously 2. So if we take the fluorine situation and just multiply this by 2 so that we have 2 fluorines, 2 times 1 is 2. And we can see that this lines up with the charge as well. So therefore, because 2 is the lowest common multiple between 1 and 2, we say that if we have 2 fluorine atoms and 1 magnesium atom, the 2 electrons that magnesium loses are gained by the 2 fluorine atoms in order to make 2 fluorines, each with a charge of -1. And if we calculate what the total ion charge is, magnesium has a charge of +2, and we only have 1 magnesium, whereas fluorine has a charge of -1, but because we have 2 of them, -1 times 2 is -2, and when we add the 2 charges together, +2 minus 2 is 0, which is exactly what we want, because a charge of 0 is what we refer to as neutral, meaning we have the exact amount of positive charge and negative charge to balance each other out and form a correct ionic bond. And we can see this if we draw the Lewis structures of 1 magnesium atom. So here we can see, with a +2 charge, magnesium has lost 2 electrons. And then if we draw not 1 but 2 fluorine ions, each with a full valence shell, we have this fluorine with a -1 charge here, and this fluorine now with a full valence shell with a -1 charge here. +2 minus 2 cancels out to 0, showing us that our positive charge and negative charges are balanced completely. And this is the general algorithm that we use in order to figure out how many metals and how many non-metals we need in order to construct a full ionic compound. To practice this, before you move on to the next video, see if you can firstly identify which element in each pair are going to lose electrons and which element in each pair are going to gain electrons, and therefore, based on that, see if you can figure out how many metal ions and how many non-metal ions are required in order to create a balanced neutral ionic compound like this. And once you have completed this, you can write the chemical formula, which is simply a list of how many metals and how many non-metals you need in order to construct the proper ionic compound. So see if you can identify what the ionic compounds are that are produced by each combination of metals and non-metals, and in the next video in this series we will look in more detail at how to construct Lewis structures of ionic compounds properly.